Hi, I'm Jakob Paul, a master's student at the Technical University of Berlin. In this video, I want to give you short insights into joint work with Georg Loho, our recent CVPR paper, Hidden Monotonicity, explaining deep neural networks via their difference of convex or DC decomposition. Attribution methods in general try to answer, given a particular prediction, which input features or evidence drove the model's decision. Gradients, CAM methods, LRP, and perturbation-based methods all give useful signals, but they can be noisy, and attribution map signs are often considered meaningless. The computation of networks with monotone components is easier to read because evidence only accumulates and gradients are also more stable. But monotonicity by design costs expressivity and is hard to apply to pre-trained CNNs. So in this paper, we ask, can we use monotonicity after the training without changing the model's prediction? From optimization, we know that ReLU neural networks admit difference of convex decompositions. That is, we can find convex networks G and H such that their difference represents the original network. In this paper, we consider a constructive algorithm that splits any ReLU neural network layer by layer into two monotone max-out networks with non-negative weights, which are colored red and blue in this graphic. We apply this algorithm to MLPs, CNNs, and residual neural networks in computer vision. To emphasize, there's no retraining, and the algorithm needs no more weight memory than the original network itself. To understand how the decomposition unfolds, let us look at how the algorithm treats the two streams at the ReLU activations. In this case, A and B represent the positive and negative streams respectively. We decompose the ReLU of their difference as the difference of their maximum and the negative stream. To study how such two monotone streams can interact, we also trained the difference G minus H of two convex networks on small datasets directly. For our MNIST models, let us take a look at the overlays of their gradients per class logit. The figure here shows an input digit 3 with the G gradients in red and the H gradients in blue. First of all, we observe that the gradients are highly class sensitive. The positive network G often seems to find the respective logit stroke in the given ground truth image, which in this example you can see particularly well for logits 0, 3, and 6. The gradients of the negative H part often focus on the missing pixels of a certain class stroke, that is, on the counterfactual evidence, as you can see here, good for logit 8. We conclude that there is a separation of concerns happening. G looks for evidence, while H looks for counter-evidence. In the decomposition of our pre-trained CNNs, we need to overcome a numerical obstacle. Since both streams have non-negative weights, there is no cancellation happening, and activations and gradients can become very large. As a solution, we propose to shift the activations and gradients of the different streams simultaneously in each layer during the forward and backward pass. The respective differences still reconstruct the original network, activations, and gradients. Using the split stream representation, we introduce three novel attribution methods. We call the plane sensitivities of the two streams split grad. Split CAM plugs these sensitivities and the split stream activations into the standard layer CAM formulas. Split LRP runs epsilon LRP concurrently through the positive and negative split streams. The stabilization parameter alpha determines the strength of shifting in the backward pass. At alpha equals to 0.5, the calculated sensitivities align with the original network gradient, while at alpha equals to 0, we are at the raw split stream gradient. Let's have a look at the results. Pointing gain peaks at 95.6% for alpha equal to 0.35 And we can also see for the other metrics that stabilization sweet spots for alpha smaller than 0.5. So how do our novel attribution methods compare to all our baselines? On VGG16 and ImageNet-S, the split methods take every Quantus category. Faithfulness, which in this table is represented by selectivity, localization, represented by attribution localization, and robustness, represented by maximum sensitivity. As a takeaway, ReLU networks hide their monotone structure, which our algorithms expose without retraining. And our methods, SplitCam, SplitLRP, and SplitCRUD, turn that structure into better explanations. If these questions are interesting to you, feel free to contact us.